So hi everyone, I'm Swagat from University of Nottingham. I'm a postdoctoral fellow here, and it's an absolute pleasure to be able to present my work at Cosmology from Home, which is one of my favorite conferences. So the talk that I'm giving today is based on a set of two papers, which is done in collaboration with these wonderful people from the UK, from US, and from India. So our best knowledge of the early universe comes from this wonderful map of the cosmic microwave background combined with BBN and LSS and BAO. So when we look at this map, two important questions come to our mind. The first one is, what is the origin of this hot dense plasma? Where from all the matter and density come from? And the second one is, what is the origin of these fluctuations that we see, these detailed fluctuations? Okay, both the questions are important. And in the part one of my talk, I'm going to talk about the second question, which is the origin of fluctuations. In fact, by now, we have measured these fluctuations very, very well. We know that the large scale structure has grown from CMB fluctuations, which can be traced back to a primordial curvature fluctuation zeta. And these initial curvature fluctuations have the following properties. They are highly adiabatic. They're almost scale invariant with a tiny tilt in the power spectrum, and they are nearly Gaussian predominantly. And even if there may be some small non-Gaussianities, so far they are consistent with being zero. Okay, so the specific properties, looking at the specific properties, motivates us that these fluctuations were created quantum mechanically during an accelerated expansion in the early universe known as cosmic inflation. So let's spend some time on cosmic inflation. So the simplest model of inflation is the following. You have a scalar field, simple scalar field phi, and it has a potential V of phi, and it's minimally coupled to gravity. Okay. In the background level, as the scalar field rolls down its potential, if it's rolling slowly, then the universe would accelerate. Okay. And in fact, if the acceleration is most of the time nearly exponential, so quasi-de Sitter expansion, and the universe expands by a factor of at least e to the power 60 during inflation. So that sets the background universe perfectly for the hot Big Bang phase. And on top of that, we have these linear fluctuations, which are created quantum mechanically. In fact, two fields are guaranteed to exist during inflation, two light fields. One is a scalar field and one is a tensor field. Okay, and you can represent them in terms of gauge invariant co-moving curvature fluctuations, which is zeta, which sort of sources your CMB fluctuations, as well as a transverse and traceless metric fluctuations, tensor fluctuations, okay, which will source gravitational waves in the later universe. So we have these two types of fluctuations during inflation, and we can predict their properties under the so-called slow roll paradigm, during which there are these two parameters, epsilon and eta, which are much smaller than 1, which simply means that the inflaton is rolling with a slow terminal speed. Okay, under this approximation, the power spectra of scalar fluctuations and tensor fluctuations, both of them, have a power law form where they have an amplitude, scalar amplitude, tensor amplitude, as well as some indices, scalar and tensor. Both scalar and tensor indices are supposed to be very small. This is the prediction of inflation. And so inflation sort of predicts small fluctuations, which are nearly scale invariant. Okay. Now, if you look at observation, we know the following, that the scalar amplitude is already known from the CMB fluctuations. And the scalar tilt is also known. It is sort of a percent level or so. Okay, it's 2 to 4%. It's a small number, finite. And so far, we have not seen any tensor fluctuations. So the tensor to scalar ratio R is at max 3.6%. Okay, so 0.036. That's great, which simply means that if you look at R versus NS plot, the data is here. Given that R is pretty small, it sort of favors this asymptotically flat potential. Okay, so the summary of this discussion is the following. Given the CMB data, the latest data, it favors single field models of inflation in a slow roll regime or slow roll paradigm, and the potential should better be concave and preferably asymptotically flat. So let's look at what are the consequences of this. So we're saying single field models of slow roll inflation. What does that mean? That means even if there are other fields which would be present during inflation, that their contribution to the T mu nu or the energy budget is negligible. Not only that, their coupling to the inflaton field would also be negligible. For example, here this G square is a coupling of the inflaton phi to another scalar field chi, and this H is the coupling of inflaton field to another fermionic field psi. Both G square and H should be much smaller, so that particle production is happening but at a negligible rate, and the accelerated expansion sort of washes out these particles, produced particles. Okay, inflation like a vacuum cleaner in some sense. What would be the effect of this particle production? Well, there would be a small subdominant non-Gaussianity, which many people are looking at. It's an exciting field. However, after the end of inflation, since the universe is no more accelerating, the produced particles can accumulate, and accumulation of these produced particles can then interact and thermalize, and that will create the hot Big Bang universe. This process is called reheating. Okay, so let's summarize what we said. So now we have this extended hot Big Bang or standard model of cosmology, in which the hot Big Bang phase is not the beginning of the universe, it's rather the end of inflation. And the transition between the inflationary phase and the hot Big Bang phase is this reheating phase. Okay, so that's the origin of all primordial matter. So that takes me to the second part of the talk, which is what happens after the end of inflation. So at the end of inflation, so initially during inflation, you have the inflaton field, which is rolling down slowly because it's friction dominated. Its effective mass is much smaller than Hubble. Then as the inflaton field falls towards the end of inflation, its mass sort of becomes important in relation to Hubble parameter. And then the inflaton field oscillates, and it's very, very homogeneous. So you have a homogeneous condensate which is oscillating. And after a few oscillations, the mass would be much higher than Hubble parameter, which is falling constantly. So these oscillations become coherent, which means that the density of the inflaton is almost a constant during one oscillation. So you can take the equation of state of inflaton and neglect the Hubble. And if the potential has a shape which is phi to the power 2n around this minimum, then the time average oscillations over a period would be n minus 1 by n plus 1. Okay, where n is this phi to the power 2n. This was known long since 1980s. Okay. Similarly, you can calculate the period of oscillations. That depends on, in general, on the amplitude of the inflaton field. A special case is when n equals to 1, when the period of oscillation is independent of this amplitude. So let's go. In fact, that's the general case that most of us are interested in, that you have an inflaton potential, which has a minimum which looks almost quadratic with maybe some subdominant corrections. If that's the case, if it's predominantly quadratic at the end of inflation, then the inflaton field behaves like matter, basically. Okay, the condensate, oscillating condensate is on an average like a matter, and that's this behavior shown in red dashed line, while this green color is the exact oscillating inflaton field density. Okay, so nice, it behaves like matter. And in this coherent oscillation regime, you can do an adiabatic approximation to say that inflaton field is oscillating like a sine or cosine with an amplitude which slowly falls because of the expansion of the universe as a function of time. Okay, so that's great. That's what the inflaton condensates should do in the absence of any coupling. Okay, we have ignored coupling, but there will be some coupling to other fields, and universe is no more accelerating, so these couplings are important. For example, in this talk, we will look at the coupling of the form G square phi square chi square between phi and chi field, where chi is almost a massless scalar field. Okay. So we have forgotten we have to couple. But secondly, let's come to the second part first. I told you that the data favors asymptotically flat potentials, and they are not like phi to the power 2n, or if you want quadratic, they are not just phi square. They have this flattened part, which leads to an attractive self-interaction here, u of phi. Okay. So the scalar field, as it oscillates after the end of inflation, it can feel the attractive self-interaction, and that would lead to a resonant growth of inflaton fluctuations. Okay, even though it's homogeneous, its fluctuations may grow as a function of time. Then maybe the inflaton field might fragment, okay, because of this growth of fluctuations. If it fragments and there is an attractive self-interaction, then the field will clump and will form cosmological solitons known as oscillons. So we will now delve into talking about oscillons. Okay, now solitons are ubiquitous in physics. They are now self-supported nonlinear solutions in scalar field theory. And well, they have been observed since 1800s, for example, by John Scott Russell in Scotland. Okay? And they appear in many branches of physics. Now, oscillons are special type of solitons. They are oscillating non-topological solitons. To give an example, if you have a potential which is phi square minus phi fourth plus phi sixth, it has an oscillon-like solution where there is a field profile which is sort of oscillating with a single frequency. Okay, to make it a bit more clear, let's look at a typical Oscillon profile, which is a sec hyperbolic field profile, where R is a radial coordinate in 3 dimensions. Okay. So it has that kind of a profile, and it's sort of oscillating. Okay, but this is an approximate solution. In general, there is a little bit of correction, which is a scalar radiation, which leaks out from this oscillon, but at a very slow rate. So these oscillons are highly stable and long-lived. Okay. Another way to think of them is to take a cross section of an oscillon, cut it into half, and see the 2D cross section. And at the center, the scalar field is oscillating with larger amplitude, and it's feeling this flat part, while at the periphery, it's mostly m square phi square. It's not feeling it. Okay. So that's the nonlinear compact object, which is an oscillon. Question: when do oscillons exist as stationary solutions of a scalar field theory? Answer: well, if there are symmetric potentials, then as long as there are these attractive terms, then oscillons can exist. For example, phi square minus phi fourth plus phi sixth has a sec hyperbolic oscillon, for example. In our work with Rafid Mahbub last year, we also showed that even if you have plateau on one side, even then you can form oscillons, phi square minus phi cube plus phi fourth, for example, and you get same sec hyperbolic type of oscillon. So great. So they exist as long as you have a asymptotically flat plateau, at least one of them. However, it's not just existence of solutions, but whether the solutions can form dynamically starting from natural conditions at the end of inflation. Okay. To investigate that, we have to study how the inflaton fluctuations grow after the end of inflation when the inflaton field is oscillating. Okay. So they satisfy this particular equation, delta phi. In fact, this is the Fourier mode of inflaton fluctuations. There is a small friction term, but more importantly, there's double derivative of the potential, which is sort of oscillating. Okay. So because of the oscillations, this is like a parametric oscillator, damped parametric oscillator. And this damped parametric oscillator would have resonant amplification. So these fluctuations would grow exponentially in certain wavelength or certain K modes, okay, frequency modes. So there are these asymmetric as well as symmetric potentials. And in for both potentials, these fluctuations actually grow. Okay, so fluctuations become higher and higher. In fact, that happens because the parametric oscillator equation in general has a time-dependent frequency term. And in such a case, flow K theorem says that you may have these exponential solutions if mu K or flow K coefficients are real. Okay, if the real part is not zero, so there's some real part, then you get resonant amplification. So it usually happens in bands of K. There are several bands of K for a given amplitude of oscillations. Similarly, for a given K, if the amplitude of oscillations is higher, then then there will be broader or narrower bands in this system. Okay, so this is very well known physics. It's a non-thermal particle production. Okay, great. However, oscillons are non-linear objects, so we can't just study linear fluctuations, growth of linear fluctuations, and be sure oscillons form or not. So you have to run lattice simulations to do non-linear, to confirm that these non-relativistic non-linear objects form in the universe. Okay. So for that, you just take your dynamical equations and convert them into dimensionless form. And in our lattice simulations, we use CosmoLattice, and we set 128 cube grid size, and we have a range of wavelengths that we integrate over in our code. Okay, so what do you see? You see that if you have asymmetric, let's say asymmetric potential, the green color is the homogeneous inflaton condensate. It keeps oscillating. And the red color are the inflaton fluctuations, which grow at some point of time and become maximum. Then they back react on the condensate, break it, and then everything sort of rate shifts as a function of time. So this is where you form these oscillons. Okay, these are inflaton fluctuations, always shown in red color, where lambda sort of represents in this potential as a self-interaction. So let's remember lambda means self-interaction. Great. You can even see the 2D slice of our full 3+1D simulations. To start with, there is the fluctuations are low, so you cannot see it in this linear scale. As time progresses, within 200 oscillations, you see the formation of these lumps. Okay, very high density. And they sort of hang around all the way till thousands of oscillations. Okay, and these are the oscillons. Very nice. You can also compute what is their overall abundance in your system. What fraction of the total density is contributed by oscillons. And we see it initially there's nothing, then it grows and sort of settles to asymptotically almost a constant value, which could be varying between 40 and 60%. Okay, so it's a significant fraction of the universe are logged into these lumps of the scalar field, whether asymmetric or symmetric potentials in both of them. Okay, so far the conclusions are following. Oscillons form in both symmetric and asymmetric potentials, starting from very general initial conditions. However, we have not coupled the system to any external field, chi, because we need to reheat the universe, we need to couple it, right? So what happens when you have this coupling and how the lifetime of these oscillons are affected? So that's our latest work, which came up in the first week of June. And there we couple the inflaton field to another field chi, and we study Oscillon formation in presence of such an external coupling. Okay. So to give you the system, we have inflaton field with potential, we have a massless chi field, and there is this coupling phi square chi square type with strength g square. Okay. And then you can write the full field equations and you can study them either in the linearism, like we are showing you here, where you have self resonance, which says how inflaton fluctuations grow, as well as external resonance, which says how chi fluctuations grow as a function of time. Okay. And you can see in this curve that it's the same curve as previously, but now we have a chi field, which is in orange color. You see that first inflaton fluctuations grow and they form oscillons, and there's some little production of the chi field also from the inflaton condensate green color. However, at some point of time, the oscillons start to decay into this chi. So it's a lot of chi production is going on. So very interesting. So you can have preheating or chi production coming from oscillon decay rather than direct inflaton condensate decay. So that was one of the great results we found. We even have a parameter space plot where I'll show you for one model. Let's say the E model or asymmetric model. Here is the strength of self-interaction. Here is the strength of external interaction. And this is a range of parameters for which we saw robust oscillon formation and lasting for thousands of oscillations. While if self-interaction is low, you don't form oscillons. And if external interaction is high, you also don't form oscillons. Okay. So this is a very interesting plot. And if you're interested, please read our paper. Okay. We also see how oscillons decay. So their energy density sort of lasts for, they're very robust oscillons, non-relativistic, and much later they sort of start to decay. Okay. And we studied their lifetime as a function of the strength of this external coupling. And we see that they go as the external coupling to the power some inverse power law, which is order 1. Okay, so that's a great result that we obtained and we're very happy about it. Finally, the fraction of oscillons in the presence of an external coupling is sort of lowered compared to in the absence of an external coupling, which is this purple curve. However, you still reach this asymptote, so you still have some asymptotically almost slowly decaying oscillons present. Okay, so summary, oscillons do form in the presence of external coupling, and please look out for our upcoming work on the phenomenology of oscillons as well as analytically deriving these results. Thank you.